A mund të qas dikush nga ty që jeni online, thjesht shoh ai u dëgjoj apo jo? Okay. Okay, so then we define the transpose of a matrix. Transpose of a matrix, this is denoted as for any matrix A, the transpose, this is defined, this is called this way, and the transpose, it is such that Aij of a transpose matrix is equal to Aj. Okay, so which means that, for example, if we have, let's pick up one of the matrices. If we pick up this matrix C, assuming that we define it here, then we may try to identify what is the C transpose, and the C transpose, we may try to, let's say, so in the new matrix transpose, every element will be, we just change the indices. Okay, so this is how we try to do this. And for example, if we're trying to identify what is C13 of the transpose matrix would be equal to C31, which means that C13 is first row, third column, and we find this element from the third row, first column. So -2 can be brought here, and similarly, this -8, the index here, it is second row, first column. Over there it becomes first row, second column, and it becomes -8. The diagonal terms, they don't change, so we have 3 to 3. Then we have 5, 7. And by the way, sometimes, if you find it a little bit counterintuitive, you may assume the following. The rows become columns. This is also another definition. So you just have a look at the first row, 3, 5, 7. This becomes a column right here. Then we have second row, -8 to 1. This becomes -8 to 1. And then we have the last number, which is
-10.
was 0. Was it 10 or 0? 0, right? I thought it was 10, 0. Okay, so this is the transpose. And so let's assume that we have a matrix E, and this matrix E, let this be, for example, -1, 2, 3. So let's try to find what is E transpose times E. What would you write for this one? What is E transpose times E? E is given.
Nossa.
Give me the area. Okay, so here, in this case, we are given this matrix E, which is 3.1, and this one, the transpose, it will be 1 by 3. So we get here -1, 2, 3. minus 1, 2, 3. 3 by 1. And then we look at the dimensions. And what would be the result?
1, 1.
It's 1 by 1. So any matrix which is 1 by 1, this is a scalar. Okay, so this is more essential than the result. We're going to get a scalar result, a scalar answer, not a vector. Well, in fact, it is a vector, but it's a vector of 1 by 1, 1 row, 1 column. So actually, we can call it a scalar. For example, number 5. This is a matrix, but it's a matrix which is 1 by 1. Okay, so this is essentially this is a scalar, and the answer it will be minus 1 times minus 1 plus 2 2 plus 3 3 1 plus 4 plus 9 14. Okay, so we learned also what is the transpose, and also just an example of how we multiply matrices. So, other than this, we talked last time about the inverse of a matrix. And the inverse of a matrix, it is defined such as the matrix A times the matrix B. This would be equal to an identity matrix I. And once we have this condition, then we can simply imply that the matrix B is equal to A inverse. So this defines this as the inverse. Now, what is, in fact, we are going to discuss how we calculate or how we determine the inverse of the matrix in details. So we'll do several examples. But for now, what is essential for us, at least we can give very briefly the definition of the determinant. Determinant është përcaktori. We call it this way. It's just a scalar value which is associated to a matrix. So if we have a matrix which is A, B, C, D, and let's call this one matrix A, then the determinant of A, which is also denoted like this would be equal to AB minus CB. So, and then there is a relationship between the determinant of A and determinant of B. So one property that we are going to see again later is that whenever we multiply different matrices, the determinant of the last one is equal to the product of the determinant of each matrix. So let's try this one in a slightly more generalized way. So we can say that matrix E times matrix F, this would be equal to another matrix G. So in this case, we can say that the determinant of F times determinant of G, this is equal to determinant of I. Sorry, G in this. No, that's wrong. E, F, yes. E, G. Now, what if this E and F, they are inverses of each other? Then this means that if G, actually this is always true. Just for a moment, let's assume that we have determinant of E times determinant of F. This would be equal to the determinant of an identity matrix. What is the determinant of an identity matrix? If we pick up a simple matrix, which is a square, which would be 1, 0, 0, 1. If we use this little formula, what do we observe? what is the determinant of this little matrix? If this is 1, 1, 0, 0, this would be equal to 1, right? So here we have an identity matrix, which we call this one I2, and this implies that the determinant of this identity matrix 2 by 2, this is simply equal to 1. So these are scalars, these are numbers, which means that if this is equal to 1, then we can say that the determinant of f is equal to 1 over the determinant of e. So they are inverses of each other. Now, once we look at this relationship, we know that division by 0 is not defined, right? So imagine for a moment what we might get if the determinant of this matrix E is equal to 0. Then that means that the determinant of this other matrix, it is not defined. So you might expect some crazy thing or something which is not very well defined in case the determinant is equal to 0, which means that if the determinant of a matrix E is 0, which can very often happen, then we call this matrix as a singular matrix. We call this one as a singular matrix, and once we have this matrix which is singular, its inverse, it is not defined. Okay, its inverse does not exist. So that's one thing that we may consider. Thanks. Thank you. So next thing that we may want to define is that matrices, they do provide for us a very good mathematical tool for to understand space, okay, or to understand the distribution of data in space. And the first step that we can use for the application of a matrix, it would be a vector. And a vector, it can be a row or a column out of a matrix, which means that one of the dimensions can be defined as equal to 1. And then what we can also, so let's say, for example, the matrix is matrix A, it looks like this, but a singular row, it can be a vector which is going to look like this. A, if it is n by 1, this is an element of Rn, okay? We call this one of Rn because that means that the number of elements in this vector is equal to this space, which means that, for example, a vector of 1, 2, this is an element of R squared minus 1, 0, 1. This vector, this is an element of R cubed. So these are some definitions. Now, once we are working with vectors, in principle, they can be, we can identify them with respect. So if we consider them in three-dimensional space, we may assume, or let's pick up this vector, for example. This is minus 1, 0, 1. Minus 1, 0, 1. If we use the point 0 as a reference point, minus 1 would be this value, 0 along the y, and 1 along the z, so it's 1 unit up here. And then, if we add these vectors, apparently, we're going to see, no, is this wrong? Let me think, x, z, yes. Okay, so in this case, what this corresponds to a vector which is on the xz plane. Okay, so this is a vector. So this is a vector in the, yes, xz plane because the projection along the y is equal to 0. Then, yes. So we have here a vector which is a sub. It's from the set of R cube. R cube it just has we have triplet of numbers. Okay. If it is R squared, we have a pair of numbers that can constitute a vector. Similarly, we can also have -1, 3. This is also a vector which is in the larger set of R squared. Okay. Now, in this case, the vectors, we can define them with respect to some origin, which is when x is 0, y is 0, and z is 0. Then we look at the first component, which is -1, and this is our 0. And we measure this -1. It's not along the increasing order of x, but from the 0, we move 1 unit backwards. Okay. The projection along the y is 0. It's right here because we wrote it 0. And the projection along the z-axis is 1. So then here we see that the vector represented by this triplet of numbers in the three-dimensional space, it's a point in the xz plane. So we can also consider the two-dimensional space or the orthogonal Cartesian coordinate system. The Cartesian coordinate system let's try to project this point. This is 1, 2. So 1, 2 is just that point in the two-dimensional space. Let's pick up this other point, -1, 3. -1, 3 is this. So here we can even call this one point A and point B. Okay, so these are vectors. Once we have these vectors, we can define some operation with these vectors, and the simplest operation with these is we can also add them. So we can define addition of vectors, and the addition of two vectors, it is such that if we add v plus w, this would be equal to v1, v2, vn plus w1, w2, wn, and this is all equal to v1 plus w1, v2 plus w2, vn, wn. So in this case, or we can simply say that the addition of these two vectors, it can be written as vi plus wi. For example, these two vectors that are written here on the board, let's say that we want to add the 1, 2 with the other vector, which is -1, 3. So in this case, so is it correct? Yes, 1, 2, -1, 3. Yes, so, and actually at this stage, we can also represent this addition, and if we follow these numbers, it looks like the addition of these two vectors in space, the result is going to be 0, 5. 0 is this point, 5 is 1, 2, 3, 4, and 5. So apparently we end up into this point. Let's call this one point C. Now, if this is vector A, and this is plus another vector B, it looks like this can be equal to another vector C, which in this case, this is the vector C, right? So this is how we can operate with these. Now, after this, we can also define this addition of these two vectors. It's not very So, given two vectors V and W, which are elements of space Rn, we can define an inner product that is denoted as shown in the board, VW, and this is also equal to V transpose times W. Okay, so this is the inner product. Now, assuming that all vectors are columns. Okay, so we pick this one by convention. So if we keep and multiply the V transpose with W, what would you say that what would you expect for the answer? So we had an example where we had the E transpose times E. What did we get? Say it again. The opposite. What about the dimension of the answer? Yes. It's 1 by 1. It's a scalar, right? So inner product apparently it multiplies because it's a kind of a product. It multiplies two vectors, and this one, the result of the inner product. So the result of this inner product, it's going to be a scalar. Now we can use these numbers here. So for example, we can take the inner product of 1, 2, with -1, 3. And this would be equal to, if we follow the definition, this would be 1, 2, this is 1 by 2, 2 by 1. It looks like this multiplication, it is defined because we can multiply these two vectors. And the answer will be 1 times -1 plus 2 times 3. This is equal to 5, that's correct? Okay, so we get a 5. Okay, it's a scalar quantity, and let me check. No, because we just take the transpose of the first one.
It's the first one.
Yeah, this is definition. We denote it like this, and we're going to see this quite a lot. Okay, so you'll see this kind of inner product definition. But yeah, we just take the transpose of the first one. Okay, then for a moment, let's have a look at the inner product of a vector with itself. So what would be the inner product of a vector with itself? Which means that here we can have 1, 2. Here we can have another 1, 2. And this would be equal to 1, 2, 1, 2. So the answer here is so here we get the 5, right? Okay. It's strange. Okay. Here we get another 5. So and the inner product of minus 1, 3 this is equal to we get the 10. That's it. Okay. Yes. Now at this stage we can also maybe it's time to define also the magnitude of a vector. So matrices they don't have magnitude, so it's hard to associate a certain magnitude to a matrix. But we can define or we can associate magnitude to vectors, and the magnitude of a vector A. Sorry, it's not a vector. This is a vector. This is equal to the square root okay, so this would be the, let's say the magnitude. And let's see a couple of examples. So, what is the magnitude of this vector? This is again, I think we did it right. That's 10. But apparently, it looks like the magnitude of A is equal to what? Square root of 10. That's true. So, in fact, in a more general sense, when I say general sense, actually, I'll talk about something which we have not covered yet, regarding the complex numbers. Complex numbers, anyone if you have seen before, you can raise your hand. Few hands, I can count them. I wish to count as many as possible. Okay, complex numbers. So it's a construct which is actually the most excellent, the most beautiful. So they compete with matrices, the complex numbers in terms of their usages. But here in this class, we're also going to see that complex numbers and matrices they have a very strong equivalence. Okay, they do almost the same thing. The complex numbers. When I asked you to give the definition of a matrices at the beginning of the class course, I might say that my choice for the matrix is to call it a mathematical construct, okay, because it's something kind of unrealistic, but it has huge usages. At the same time, complex numbers are also mathematical construct because it's something stupid. It is the square root of minus 1. Okay, we just call it I. So this one we're going to see them. So this is really a mathematical construct. This has endless applications. This has several usages. And why do I mention this one here is that we are going to see later on that always the magnitude of any vector which can have also complex numbers, it is going to be represented like this. So if you have a vector A, and this vector A can be 5 minus 5i plus 4, where I now is that unique odd number. So if we want to find the magnitude of this vector, all we do is always we multiply the complex conjugate of this vector with itself, square root. This would be the magnitude of any vector, which is not only real number, but also complex numbers. So far, we are considering that these vectors are subsets of R squared, but they can also be They can also be complex numbers. Now, it happened 3 years ago that I taught algebra to an electronics group. When they came to antenna theory in the 3rd year, I said, "You remember somebody told you linear algebra and wrote something like this on the board? Probably you forgot it." So this one, you're going to see this a lot, but it will be a combination of a little bit of matrix knowledge we're covering right now, plus vector notation, plus complex numbers. But don't worry, for the moment, this would be the most generalized form of determining the magnitude of some quantity, which are very useful. But the same way here, we're just assuming that we're just going to calculate the transpose. This notation is something that you can just write down on your notebooks. This is called complex conjugate of a number. Okay, complex conjugate. Yes, that one at the start. This will be defined as something like this. In case A, it's a complex number which is 3 plus 4i. The complex conjugate, this would be equal to 3 minus 4i. Okay. So for a while, if we want to find the magnitude of this vector A, for any one of you that might have seen this before, is that we will just have to multiply these two together. If we multiply these two together, let's see what we get. We get 3 plus, no, let's do minus 4a minus 4i times 3 plus 4i. So what is the product of these two numbers?
3 squared minus 4i. It's a squared minus b squared.
Right? Okay. This is 9 minus 4i squared. But what was I squared? Okay, x minus 1. So this is equal to 9.
Isn't that 16?
Which one?
4.
Of course it is. Yeah, for sure it is. It should be that way. That's a mistake. It was 16. This is equal to 25. That is good. So what this is the magnitude of some complex number. At the same time, yes, I'll just finish it right here. You are right for reminding me. Just assume now this was a complex number. We use a little trick. Now let's assume again if we have a vector which is 3, 4. 3, 4, 1, 2, 3, 4. Assume that we have a vector E which is equal to 3, 4, and then I can ask the same question. What is the magnitude of this vector E? The magnitude of this vector E, this would be equal to the transpose of this vector. What is the transpose of 3, 4? Yes, 3, 4. Then here we get 9 plus 16. Actually, we should include square roots everywhere. So this ends up into being something like equal to 5, right? Yeah. Which is something similar to here, because then the magnitude of 3 plus 4i, this would be equal to 5. And similarly, the magnitude of this vector E, this is equal to 5. Now, what is the magnitude of this vector 3, 5, 3, 4? This is the length of the vector. Using Pythagorean theorem, a squared plus b squared is equal to c squared. We see that in this case, the length of this side is equal to 3, plus the length of this side, which is equal to 4 squared. This would be equal to the length of this vector, hypotenuse, which is equal to 5 squared. If you want, we can have a short break.